Okay, so this is the second hour of Physics 1C for May 12th. And the next thing we're going to be talking about is, a couple things. We'll come back to that later. Next thing we're talking about is going to be a capacitor in an AC circuit before we put all these things together. So, yeah. This would be voltage source, capacitor plate with capacitance C, and of course this is a voltage as a function of time, and there's also going to be some voltage across the capacitor right here as a function of time that we're ultimately going to want to know. And again, we're going to start off with the assumption that the current as a function of time in our system is going to be given by some max current multiplied by cosine omega t, just as we've been doing before. Ultimately, we're going to want to put all three of these things together, so having the current in each case be the same is going to be pretty useful. Okay. So having a capacitor in an AC circuit is quite a bit different than really any of the capacitor stuff we've seen before. So the current at a moment in time in this circuit we represent, as I of t. And because the current is oscillating back and forth, what that means is that sometimes the current is going to be pushing positive charges onto this plate, and sometimes the current's going to be pulling positive charges off the plate, which means that the capacitor itself is basically going to oscillate back and forth between this plate. If you look at what's happening on just the left plate, it's going to go positive, negative, positive, negative, positive, negative, right? And what's interesting about this compared to a DC circuit is that in a DC circuit, what the capacitor does is it effectively stops the flow of current in the circuit, right? It acts as a thing that kind of hold charge, but it definitely stops the flow of current eventually. That does not happen in an AC circuit. In an AC circuit, the capacitor basically just acts effectively as a springboard for the charges. And it has the effect, once it's fully charged, of producing an EMF opposite to that of the battery. Meaning that if the current is flowing in this direction, that means that this side is positive and this side is negative at that moment in time. So as the capacitor charges itself up, it's eventually going to push backwards on the battery. Now, what we know about a system like this is that the voltage across our capacitor is related to the charge on the capacitor, so let's call the charge on the capacitor in a moment in time Q. Is it divided by the voltage? I always have to think about this. It's Q equal to C times V. So the voltage, it's Q divided by the capacitance, right? And if we know what the current as a function of time is, we also know that that current as a function of time can be expressed as the time derivative of the charge, dq dt, being equal to this. And we can use this expression here to solve for what the charge as a function of time is, because that's ultimately what we need over here to find the voltage across our capacitor. We do that by doing a separation of variables. We say that our expression here tells us that dq, not dg, dq would be equal to that dt. And then what we'll do is we'll just integrate both sides of this to find the charge as a function of time. We'll integrate from 0 up to some q prime, and we'll integrate over here from 0 up to some t prime, which just represents some arbitrary time in the system. The left-hand side of our equation is going to become q prime, and the right-hand side of our equation is just going to become, well, we're taking the integral of cosine, so we're going to get a sine of omega t, right? We're going to have our I max here. We need to divide by the derivative of the inside omega right here, and then I guess that just becomes t prime. Right, that's the integral of cosine. So this tells us that we have an expression for the charge as a function of time now, right? Charge as a function of time on our capacitor is going to be given by I max divided by omega times sine omega t. We can plug that into this now to see exactly what the voltage across the capacitor is going to be. It's going to be I max divided by omega from here times c from here multiplied by the sine of omega t. And now what we'll do is we'll make the statement that sine omega t I believe there's an identity that says that this is equal to the cosine shifted by pi over 2. But there's a minus sign now. Does that look right to you guys? Sine omega t is equal to cosine omega t minus pi over 2. Which means that we can now state that our voltage across our capacitor as a function of time is going to be equal to I max times 1 over omega c, capacitance, multiplied by now cosine of omega t minus pi over 2. Now, what this tells us is that our voltage across our capacitor is now going to be related to the current across our capacitor. So there's our current. See, that's a cosine function. This is a cosine function that's been shifted to the right by pi over 2. So that effectively means that the voltage lags the current by a quarter cycle. What we get out of this is that the voltage across the capacitor lags the current by a quarter cycle. Just to kind of tie this back to what we did a second ago, voltage across the inductor has a head start. Voltage on the capacitor lags the current by this much. Okay, we can put that into a phase diagram. And on our phase diagram, we'll start off by drawing our current. So let's say that our current at a moment in time, I believe we've been using blue for current. Our current is a function of time. Here, we go shapes, we get this shape, and we try to draw an arrow like that. And then I just do what? I hold Alt, and I drag. Why isn't that the default, by the way? You got disconnected? Is my stream still going okay? Looks like it is. All right. So that's going to represent our I max for our phasor. We again say that the angle made right here is going to be omega t. And now, in order to get my voltage phasor, the voltage phasor is going to have to come down. Let's use green. The voltage phasor is going to have to come down like this. That's not a shape. I want a shape. There we go. Voltage phasor is going to come down like this. And it's going to need to make a right angle. That looks like a right angle. We shift this vector up a little bit. Again, holding Alt to do this. So there's our voltage phasor. That's going to be a length of V max. And yeah, that's going to be omega t minus pi over 2, basically, right? That's what this angle down here now is going to be omega t minus pi over 2. It's a negative angle, so it's just yeah. So I guess it depends if it's negative on sorry. So that's our relationship now, right? That's what it looks like. The voltage lags behind the current. Now, why would that be the case? Why would the voltage lag behind the current in the case of the capacitor? Specifically, the voltage across the capacitor itself. You guys have any idea? I don't know if it helps to plot it like this, but if we plot ooh, that's not what I wanted to do. I'll just make it black again. If we plot on a diagram, our current is a function of time. Oh no, it always does that. It's so annoying. Click, and then I go blue. And then here, if I plot the current as a function of time, the current as a function of time was a cosine curve, right? And we need to have the other one be cosine omega t minus pi over 2, so we have to shift this curve over by 90 degrees, so it becomes effectively wait a minute. Oh, you shift it to the right. Right? The negative sign, you shift to the right, my bad. So this whole thing would have to get shifted to the right. So let me draw the other piece of this so we can see it. Yeah, I can see how it's going to happen now. We shift this to the right by pi over 2. So now it's going to be a sine function. There we go. That makes more sense. It's going to reach maximum there. It's going to reach a maximum whenever the other one goes to 0, and then it's going to dip to 0 here, and then a maximum there, and back to 0 here. So that's going to be our current, and then this is going to be our voltage across the capacitor. Why would the voltage across the capacitor, let's say, be 0 when the current is maximum? That makes sense? So this represents Imax, and this represents V equal to 0, right? Why do those two correspond to each other? Why is it that the voltage across the capacitor is 0 when the current is maximum? Does that make sense? Why is the voltage across the capacitor 0 when the current is at maximum? Yeah, that's a good way of putting it, Quincy. The current is already flowing, but the charges are just collecting on the capacitor, exactly. And what happens to the current as the charges build up on the capacitor? Well, when the charges start to build up on the capacitor, like once you get to, for example, here, when you're at your maximum voltage, that's also the maximum charge, right? It's max voltage and max charge at the same time, right? Well, if you have maximum charge on the object, then your capacitor is effectively pushing back on your current. And that's why the current drops to 0 at that same time. Because you can no longer have current flowing at that time because the capacitor maybe is fully charged at that moment, right? But then the current basically starts to flow back in the negative direction, right? And at that time, while the current flows away, eventually, when it's negative current here, then you get 0 charges on the capacitor at that point, right? So there you go. The voltage on the capacitor lags the current by pi over 2. Go back here. Voltage across the inductor has a head start on the current by pi over 2. And then with resistors, the voltage is in phase, right? And when we put all of those three together, we're going to get our LCR circuit that we can investigate, and that's what we'll do next. Okay. Does anyone have any questions? Yeah. Yep. Current maximum means you have charges flowing directly into the capacitor. And you understand that means the capacitor is going to have charges stored on it over time at that point, right? As those charges build up, the capacitor represents an opposite voltage to the battery, right? Like if the current is flowing in this direction, then this side of the plate is going to become positive, right? But if the current was flowing that way, that must mean at that moment in time that this side of our voltage source is positive, right? So when you have positive here and positive here, you're going to have a breakpoint, right? Where once those charges from this current here flow onto the capacitor, they're now going to want to push back in the opposite direction, right? The capacitor acts, as I said, as like a springboard for charges. You push as many charges onto it as you can, but eventually it's going to push back on you. And at some point, there's going to be a balance between the applied current and the voltage that's pushing back from the capacitor. And that's when you get 0 current and maximum charge, right? Now, once these charges have flown out of the system and they've flown back to 0, you get the current flowing back in that opposite direction. Did that answer your question? Okay. Again, the best analogy for what a capacitor does in a circuit is this, right? So you start off with an object that's a mass on a spring, right? It has some mass. You have a spring constant K, right? And you take this object, right, and you stretch it out to some point right here, right? Now, if you let it go, it's gonna oscillate back and forth and back and forth and back and forth like this, right? And when you get to the center point right here, at that time you get maximum velocity, right? This is, to tie the analogy together, this is like max current. Well, what happens when this object is moving with a maximum velocity this way, right, when it passes through what we call the equilibrium position? It has inertia, so it has the effect of then compressing the spring to some position, right? The spring has some energy, though, and that's going to cause it at some point to turn around and go back the opposite way, right? That's exactly what's happening in this system right here. You just replace the box with a charge, the velocity with current, and the compression of the spring gets replaced with the amount of charges that are stored up on this object right here, basically. Does that analogy make sense? So it's like you push the charges into the capacitor, it acts like a spring, it gets compressed to its maximum amount, at which point it pushes back in the opposite direction, right? And I could draw the exact same representation right here if I simply replaced current with velocity and I replaced voltage across the capacitor with compression of the spring. You see what I mean? You literally would plot the exact same thing. The relationship between the position of the objects and the velocity of the object is that one is the derivative of the other one, right? It's literally, this is it. I mean, it's velocity is equal to the derivative of current position, right? And current is equal to the derivative of the charge, right? You can immediately see the connection between these two. X is mapped onto Q. This is velocity, by the way. How do you draw velocity? I don't know. Right? The current and the velocity are like the same thing. The charge on the plate is the same thing as the compression of the spring. And they have this relationship. Okay. So I kind of want to make a little table here. Oh, one last thing I forgot. This piece right here that I intentionally wrote like this. The voltage across our capacitor, right, is related to this quantity here. And this quantity, let's copy it and paste it down here. It represents the maximum voltage across the capacitor. This is basically Vmax across the capacitor. And what we want to do now is we want to replace that term right there with the symbol x sub c. X sub c is basically going to be equal to 1 over omega c. And this is, that's a definition. This is called inductive, no, not inductive, capacitive reactance. And with that definition, we get that the voltage across the capacitor is basically equal to I max multiplied by x sub c. This is a capital X. There's your relationship for your voltage across the capacitor. And what it tells you is that the output current in your system, the maximum current in your system, is reduced by this quantity. So this is Vmax across capacitor. It's reduced by x sub c. And what is x sub c? Well, you can see right over there what it is. It's equal to omega c, right? So what does this mean? If we think about what this quantity does, this quantity is going to be large when omega is small, and it's going to be small when omega is big, right? So if omega big, then look at this expression here, then I max is small. And if omega is small, well, you get the opposite. That means that I max is going to be large. Right? Now, why would that be the case? So omega is the frequency, right? It's the rate at which the power source is pushing charges back and forth. In America, it's like 2 pi times 60 hertz. Okay? The larger that quantity is, right? The larger that quantity is, oh, wait. I got it backwards. I was about to say something that sounded not true to me. Yeah. It's kind of weird. I also wrote it over here wrong. My bad. Let me slow down for just a second. Let me fix this. XC is 1 over omega c, right? So that means when I put this in here, it's a Vmax divided by 1 over omega c. Which means that when omega is big, right, XC is small. As a result, I gets big. So I got these backwards. This is actually large. So this would be if omega is big, then Imax is big, and if omega is small, then Imax is small. Oh, man, I'm trying to crunch too many things in a small location to fix my mistakes. That's bad. That's what I wanted to say. If omega is big, then this quantity is going to be small, and as a result, Imax will be big. If omega is small, then this quantity is going to be a big number, because it's in the denominator, and then this is going to be small as well as a result. Now, why would that be the case? If omega is big, if this is a large number, then xc becomes a small number, and if xc is a small number, then this becomes large. If omega is small, xc becomes big, and if xc is big, then Imax is going to be small. Yeah, that's right. So why would that be the case? Why would it be a case that the capacitor would do more when the frequency is large? Or sorry, why does the capacitor I should put it this way. Why is the current large? There we go. Higher frequency means that the capacitor has more opportunity to put current in the system. What do you mean by that? That's kind of close. What do you mean by that exactly? The capacitor is charging up and discharging more often. That sounds about right. Now, it also depends on C too, right? I mean, the smaller the value of the capacitance, the bigger this becomes. What about the opposite? Maybe it makes more sense to think about why is the current okay, if this is small, this becomes big. Oh, I didn't mean to do that. Basically, what these things say is that when the frequency is large, the capacitor doesn't do as much. It has less effect on the system. But when the frequency is small, why do you have this reduction in current then when the frequency is really small? What does that mean? Let me ask this question. What would the frequency be if it was a DC circuit? how long would it take for it to repeat the cycle of turning on and off? What kind of frequency would we use to represent a DC circuit? How often does a DC circuit oscillate back and forth? It doesn't have frequency. Exactly. The answer is 0, right? Not 9, 0. Be 0. What would XC be? In a DC circuit, what would XC be? Yeah, infinity, right? So what's I max? It's 0, right? It's 0. Does that make sense? If I take a circuit and I connect it up to just a DC circuit, so I have a battery down here, right? We know that what's going to happen basically is this plate's going to charge up until it has the same voltage here as you have here. And there's no current, right? I equal to 0 in the system, right? That would be your DC circuit, right? The capacitor would quite literally block all current flow in the system, right? So now let's go back to this question. If I have an alternating circuit, but the frequency is really small, like maybe 1 hertz or something like that, why would that lead to a smaller current? Here, what does it say? If it takes longer to store the charges and changing slower with respect to time, so low frequency leads to low current. That's a good way of putting it. If you have a low frequency, you have a longer time, that's what he's saying, a longer time to store the charges, which means the capacitor is going to do more, right? The capacitor it does the most work in the system, or it has the most effect on the system when it's allowed to be fully charged. And if the system is charging up slowly, because the frequency is slow, then the capacitor is going to build up that kind of opposite EMF more quickly. And once the capacitor is fully charged, well, that's like the compressed spring, and it's going to start pushing back on you. So effectively what these things, the reactance things, do is they describe the effect of having one of these objects in your system. When you have a capacitor in your system, you can say that capacitors effectively tend to slow down or resist low frequency current. What do inductors do? Inductors care about the rate of change of the current, so they resist high frequency current. And what does a resistor do? Resistors don't care if it's low frequency or high frequency, they resist all current, regardless of if it's high frequency or not. Does this kind of like idea here make sense to you as to like what these things are doing? You've got your capacitors, you've got your inductors, you've got your resistors. They each do different things. The capacitors resist the low frequency current, the inductors resist the high frequency current, and resistors resist all current. Okay? I can give you a really, I don't know if it's simple, but maybe it'll be simple to you guys. Do you guys ever heard of an equalizer before? Do you guys know what an equalizer is? It's like something that you have in audio systems. Do you guys know what I'm talking about? So you can find a picture of one for you guys here. I'm sure you'll recognize this as soon as I pull it up. Got a lot of images of a Denzel Washington film. Okay, so it's these things. You may have seen it on, I don't know if you have any kind of these things right here. Do those look familiar to you guys? Like this thing right here? If you go into an audio store, you'll see these kind of devices on higher tech audio equipment. If you have a program like Winamp or any of your type of program that like controls audio and stuff like this, you'll have something inside of here. And what do these things do? What do these little things do here? Looks like this is an equalizer you can get as an app on Google Play. You've got 32, 64, 130, etc., up to 816K. What do these numbers represent? Does anyone know? Frequencies, right? High frequency over here and low frequency over here, right? What do the low frequencies sound like? Deep, right? Bass sounds. Like, think like hip-hop with, like, really deep, yeah. Makes the music sound good, exactly. What do these ones do? What do the high-frequency ones do? Those are, like, the soprano sounds, the high-pitched sounds, right? They sound like your little brother yelling. Is he like, 11 years old or something like that? High-pitched, right? Over here, you've got high-pitch, and over here, you've got low-pitch, right? They're related directly to frequencies. So you know how these things work? They use inductors and capacitors, okay? So the ones that put out, if you want to raise the high-frequency sounds, what you need to do is to make the sound that's the current that's producing that sound, you know, you want to let it through, right? You want to let through the high frequency current, right? So what would you do to let through high frequency current? You lower the inductance of your system. If you lower this, right, then you allow the high frequency stuff to pass through, right? Or if you raise this, actually, you can raise the capacitance. By raising the capacitance, you're going to have high frequency coming through, right? Quite literally, that's what one of these devices does, is it modifies the capacitance and the inductance within your system in order to modify the current flowing in the system, and the current flowing in the system gets directly turned into sound that you hear, basically, right? And the things that you're going to hear are the things that have the most noticeable sound, right? Which will be the loudest sounds. And if you resist the high frequency current, you're going to get bass sounds. If you resist the low frequency current, you're going to get high pitched sounds. Does that make sense? So this is like the treble knob on old simple, and this is like the bass knob. Whoops. This is like the bass knob right here, right? If you crank up the inductance, you're going to get a lot more bass because it's gonna block out the high frequency sounds, the high pitch sounds, right? And if you, I hope I'm getting this right, if you increase the capacitance, it's going to lower the bass sounds. It'll bring out the higher pitch sounds. Does that make sense? So if we go back to our picture right here, these are like increasing capacitance over here, and these are basically increasing inductance. Does that make sense to you guys? Was that too complicated? I don't know. I know this stuff is all really tricky and hard to understand, but that's one example of what these things can do. Okay. Okay. Now we can put all this stuff together. And I think I'm just going to kind of type out in a table what we know right here. So we have basically a set of things here. We've got a circuit element. We've got an amplitude relation. We've got the circuit quantity. And we've got the phase of the voltage as a function of time. And the way that these go are, we've got resistor, the resistor has an amplitude relation that we learned long ago, which is just that the voltage across the resistor is equal to IR. The circuit quantity is just the resistance R, and the phase here is in phase. For the inductor, what we have is V sub L is equal to the current multiplied by X sub L. And then the circuit quantity is this thing X sub L. And we saw that that was equal to, it's not going to let me do that. We'll just put a W, omega times L. And this one happened to say that the phase of the voltage is that it leads the current by 90 degrees, or pi over 2. Okay? Now there's actually something that we can use to remember this, and what we use to remember this one in particular, oh, whoops. I want to add one more, can I add like a cell? insert 1, right, there we go. So what I want to put over here, one way we can remember this for the inductor is this right here. It stands for ELI, stands for the EMF leads the current. That's what that means. For the capacitor, we have V sub C is equal to I times X sub C, where X sub C is equal to omega times 1 over omega C. It's 1 divided by omega times C. And this one lags the current by 90 degrees. And our way to remember this one is ICE, which stands for ICE. ICE stands for the current leads the EMF. This is for a capacitor. That's what the C stands for. And this one is, this is for the inductor. And there's a mnemonic to remember all of these. Eli the ice monster. Something I guess I learned a long time ago. This is kind of a summary of what happens in an AC circuit right here. You've got resistors, inductors, capacitors. One is VR equal to IR. This is VL equal to XL. VC equal to XC, or IXC. And then this is what the quantity is, and this is the summary of how they all work. And we can take all these together, okay, to describe what happens in what's called an LRC circuit. And that's exactly what we're going to do next, is we're going to take all of these things that we've done so far, and we're going to construct what's called an RLC circuit. Specifically an Rlc Series Circuit. This is the vast majority we haven't done a single problem so far this class, right? And it's because we need to get to this final point right here to really do the problems that we want to do. So an Rlc Series Circuit would look something like this. You'd have your voltage source, right? And connected to this, you just make a series circuit. So you're going to have resistor, inductor, and a capacitor, all connected in series. So C, L, R, with a current flowing through the system. And again, what we're going to do here is we're going to say that the current as a function of time is given exactly as we did before. So I of t is going to be equal to what I max multiplied by the cosine of omega t. Okay. And now what we're going to do is we're going to consider what happens to the voltage across all of our pieces right here. Okay. We're going to say that the way to analyze what's happening here is to realize that if I want to find the voltage across each of my elements here, and I want to do that by measuring what their voltages are, what I would do is I would connect up a voltmeter right here, and I would say that this voltmeter is going to read out V sub R. If I connect a voltmeter between here and here, this voltmeter is going to read out V sub L. And if I connect a voltmeter between here and here, that it's going to read out, oops, my bad, V sub C. And then ultimately what we'll want to do is we'll also want to read out the voltage here. And we're going to call that the voltage across the source, Vs. Now, if you look at the way this is designed right here, the way I've set this up, we get different readouts for each one of these, right? Depending on what the resistance, the inductance, and the capacitance are. And all things being equal, if we didn't know what we knew already, you might think, well, should it be the case that Vs should be equal to Vr plus Vl plus Vc? Oops. Oh, plus Vc. It seems like that might be the way you would want to do it. They are in series after all, but this turns out to be not true. And instead, what we have to do is we have to use our Phasor diagram to fully understand exactly how this is going to work. So let's draw our Phasor diagram in here. Nope, not that one. That one. And let's draw out each of our individual arrows. The first thing we're going to do is we're going to start off with an arrow to represent our current. And we'll use green for that one. No. Stop. I don't like the way OneNote does things. So we're going to go green, and then we're going to go shape, and then we're going to draw an arrow like right here. This arrow is going to represent our current in our system. And I'm just going to put it right there on the axis to make this really simple. So that is our current phasor. And now what we're going to do is we're going to put all of these things that we have up here into part of this. Let me just scroll up just a little bit so we can see it all. So the resistor, right? If I want to draw a phasor to represent the voltage across the resistor, this is what it's going to look like. The voltage across our resistor is going to be in phase with that current in the system, right? So let's draw an arrow right here, as parallel as I possibly can. And we'll pick that arrow up, and we're going to move it right on top of this one here. And say that that little purple thing right there is going to represent the voltage across the resistor. Okay. Now, we know that for the inductor, that the voltage across the inductor leads the current by 90 degrees, right? So if I want to draw an arrow to represent my inductor right now, what I need to do is, let's use orange for this one. So this is going to be orange for this guy. And we're using purple for this guy, just so it's clear. For our inductor, what we're going to get is it has to lead the current by 90 degrees, right? The EMF across the inductor leads the current, okay? So that means that it's going to be an arrow. No, not like that. I don't know why I did that. I'm going to have to click shapes again, click this. So I draw an arrow straight up like this. A little bit longer. Why did it have to tilt just a little bit right at the end? Shape, arrow. Why does it do that? That's weird. Okay, arrow, straight up and down. There we go. And now we take this arrow, we're gonna move it to here. And we're gonna say that this represents V sub L. Next, we do the capacitor. We'll use like blue for the capacitor. The capacitor lags the current by 90 degrees. Well, the current is in this direction, right? So we're gonna draw our capacitor as having a voltage phasor that goes down like this. This is the whole reason why we even did these phasor things. Okay, hold Alt, and I drag this here. And I want to make this one, no, not like that. I don't fully understand. Okay, there we go. That's fine. That's fine right there. So that is the voltage across the capacitor, all right? Now again, we imagine that all of these phasors are rotating like this at a rate that's equal to omega t, but we're just looking at them at one point in time, okay? That's a combination of all of our phasor diagrams. Now what we're going to do is, in order to find the voltage across the source, what we're going to do is we're going to copy this guy. Well, I don't even know if I can do that. I'm going to draw one more phasor on here, drawing in black. So now I'm going to draw a phasor, and I'm going to say, since the voltage across the inductor and the voltage across the capacitor point in opposite directions, if I was to add the voltage across the inductor plus the voltage across the capacitor, what I would get is VL minus VC. Because they're already in phase with each other, or one is up and one is down, I can just draw a line here that's basically the difference between the two of them, and that looks roughly okay. And that's going to represent VL minus VC. That right there is going to be equal to, I don't know if it's exactly right, that's what's going to represent V sub L minus V sub C. Now the final thing we want to do now is to draw a vector, and we're running out of colors here, so let's do one that's like yellow, I guess. I bet yellow's not going to show up well, actually. We'll do, I've already done green. Purple? Now we draw a final phasor to represent the voltage across our source. And that phasor is going to look like this. I don't know if I made it long enough. I really didn't, I don't think. It needs to go to here. And then now, how do I? Oh, there we go. Okay, I just need to do like that. So it's going to be something like that. And to just get it right, what I'll do is I'll copy this one. And we'll paste it over here just to make sure we got it just right. Alt this. There we go. And then we click on this guy, and then Alt, and we go like that. There we go. Perfect. I'm going to say that this one represents the voltage across the source. And this angle right here, we're going to call phi. And I'll just indicate over here on the side by erasing that stroke and that one. No, I just want to erase that. I'm just going to label, or I can do like this, I guess. Just so it's clear that this represents VL minus VC right here. Okay. And now we're going to do some math with our Phasor diagram here. Okay. What we're going to say is that if I want to find the voltage across the source, we'll use this one. If I want to find the voltage across the source, I would argue that we can use the Pythagorean theorem. We have a triangle here. It's a right triangle. And we can say that basically, if I take VR squared, and I add to that and I take the square root, would you guys agree that that's what I'm going to get? Just the Pythagorean theorem. Whatever the length of this side, VR, is, and whatever the length of this side over here, VL minus VC, I can do this squared plus this squared, and I'll get this because of the Pythagorean theorem. So now what we could do is to remember what each of these represent. So V sub R, right, is IR. V sub C is I times XC. And V sub L is I times XL. And now I'm being a little bit sloppy here. What I'm going to say now is that these could all be either maximum values or they could be RMS values. It doesn't really matter. This is either Vmax over here and Imax over here, or it could be VRMS and IRMS. It really doesn't matter. But this is our relationship with how these things work, okay? So now what we get is that V sub S is going to be equal to, so VR is IR, so that's going to become I squared R squared, plus in here we're going to have VL is going to be I times XL minus I times XC. And then that whole thing is squared. So if we want to pull the I out, we get I multiplied by the square root of, let's see, is it R squared plus XL minus XC squared. See, every term has an I squared in it, right? And then the square root of that is going to be equal to the voltage across the source. And now we can say that Vs is going to be equal to I multiplied by this quantity, but we're going to define that quantity to be Z, where the quantity Z is defined as the square root of R squared plus XL minus XC squared. And we call this impedance, or impedance. Oops. This is effectively like a generalized type of resistance. To include inductance and capacitance into defining what happens with the circuit. And you get this really nice, simple relationship here, which tells you that the voltage across the source, I'm going to write it in a slightly different way. This says the voltage across the source divided by the impedance in the system gives you the current that flows through the system. And this could be max current, or you could write the exact same thing down for RMS current, because RMS is just taking Imax and dividing by root 2. So you could also get RMS current out of this as well. Okay, this is a very simple relationship, right? The bigger the value of Z, the lower the current output. The smaller the value of Z, the larger the current output. It's just that simple. Does that make sense? We can write it also like this. So if we take V source RMS and we divide this by square root of R squared plus XL minus XC squared, you can actually see exactly what it takes to get the maximum output current, right? How do we maximize the output current? what causes the RMS to go to maximum? Suppose I have a resistor, and I have an inductor, and I have a capacitor. What is it that actually maximizes the value of the RMS current? The smallest impedance possible. And what could be done to lower impedance? Suppose I have a system, okay? And let's say that I can manipulate anything that I want within the system. I can manipulate the inductance. Yeah, he said it. That's not quite right. Did you mean this? It's when these are equal to each other, right? That what you meant, Quincy? It's when these are equal to each other, so that term is 0, basically. Okay. We call that a resonant system, and we'll talk more about that later. But yeah, we've got our definition of what RMS, what impedance is, basically. And there's one other thing we need to calculate here that we're going to need to have for this type of system. We also need to calculate this quantity right here, phi. And that's relatively easy to do. We can make the statement in our picture right there. And I'll draw it down here. That basically the tangent of phi is equal to, I think it's basically like this, VL minus VC divided by R. And I'll go back to my picture so you can see that. Let's actually just copy this. And then come up here and put it beneath here. And then just make it smaller. Can you guys see that from the picture? The tangent of phi would be this side divided by this side, right? So VL minus VC is the opposite, and then V, yeah. Can you guys see that right there? Oh, whoop, 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 whoop. That's not quite right. Not the R. That's wrong. It's not R, it's VR, my bad. It's the voltage across the resistor here. I skipped a step. It's VR. And now all we do is we plug in VL was I times XL minus VC, which is I times XC, and we divide that by I times R. And that gives us that the tangent of phi is equal to XL minus XC divided by R. What is phi? Phi is a phase angle, and it's actually going to have an impact on the system that we'll describe here in a second. It's directly related to how efficient your system is. And the closer that phi is to 0, the more efficient your system is going to be at outputting current. And we'll see why that is here in a second. In fact, you can probably see that phi equal to 0 would correspond to the case in which XL is equal to XC, right? That's when you're going to get phi equal to 0. But we'll do some problems with this, and we'll come back to describing what it is. We also need to define what power is in a circuit to really get there. Okay. I think we have everything we need to have to do this problem that I want to do now. A lot of theory, all to solve a problem that's going to take us like 5 minutes to solve. I hope that some of this has made sense. I hope that, if you do have any questions, feel free to ask. But I guess I could stop for just a second and say, like, looking over this discussion about impedance here with RLC series circuits, do you have any questions? The biggest things to take out of this are this equation right here for impedance. Okay, I really should have boxed that one in. The definition of impedance, the relationship between the voltage, the current, and the impedance, and then what the phase angle phi is right here. The phase between the voltage of the source and the current. Okay? Any questions? All right. This is one of those problems where, like, you guys actually already know how to solve this now. And so I'm going to have you guys be the ones that solve this one, okay? So here's what we have. We have a series RLC circuit that has a resistance of 425 ohms, an inductance of 1.25 Henry, and a capacitance of 3.5 microfarads. It's connected to an AC source with a frequency of 60 hertz. In case you can't read all this stuff, it says that the resistance is equal to 425 ohms. It's not that one, we want the one that's like a little bit smaller. It says the inductance is 1.25 Henrys. The capacitance is 3.5 microfarads. The AC source has a frequency that's equal to 60 hertz. And delta V max, so I've just been calling this V max. It's from a different textbook. This is equal to 150 volts. We want to find the inductive reactance, the capacitive reactance, the impedance, the maximum current in the circuit, the phase angle between the current and the voltage, the maximum voltage across each element, and then something else at the very end. We're going to go through these one at a time. So I'm just going to put the equations that you need down here, and I'm going to have you guys try to calculate it. Inductive reactance, that's this one. XL is equal to omega times L. Inductive capacitance, that's XC, is equal to 1 over omega C. You get values that are in. And then impedance, right? Okay, so the impedance calculation was Z is equal to square root R squared plus the inductive reactance minus the capacitive reactance squared. Maximum current, you get maximum current by saying that Vmax divided by the impedance gives you the current. Maximum voltage across each element. To figure that out, for example, V sub R is just IR. VL is I times XL. And VC is I times XC. Oops, get ahead of myself. I times XC. This is a 100% just plug and chug problem. Oh, and I guess the last piece is that omega is equal to 2 pi times F. I want you guys to try to solve this so you can get an idea of how you do these kind of problems. And I'll give you a few minutes to do so. Okay, so do your best, see if you can solve these, and then at the very end, we will answer part E. Okay, can you guys give it a shot? Do you have enough information? All right, see if you can solve these. Feel free to ask if you have any questions. Is that enough time? Have you guys been able to solve all of these already? Or do you need more time? Tell me, what did you guys get for these values? Like, what did you get for almost done? Okay, let's see how far you guys have gotten so far. What did you guys get for x of L? Let's put out, it's omega L, right? So omega was 2 pi times the frequency, which was 60 hertz, right? Hertz is cycles per second. Multiplied by L, and L is just 1.25. So that 5 over 4 times this is 5 over 2. 30 times 5, 150, 150 pi, something. Something like 500, okay, 470, yeah. Okay. Oh, that's Henry's right there, my bad. And then what about XC? XC is, what is it? It's 1 over omega, which is 2 pi, times the frequency, which is 60. And then multiplied by 757, okay. That's times C, which is 3.5 microfarads, so that's going to be 3.5 times 10 to the negative 6. This is 757. Do you guys agree with that? Sounds right to me. What else we got? The impedance, right? Okay, so impedance is going to be the square root of r squared, so that's 425, plus xl minus xc, so that's going to be 471 minus 757. Did I already make a mistake? We take this, that's squared, and then we take the square root of it, and that's all going to be with a symbol of ohms at the end. 512, is that what you got? Let's see. So that makes sense, because this is going to be about 300, so 400 squared plus 300 squared should be about 500 squared, right? It's like a 3, 4, 5 triangle, not quite, but close. Is that right? And that's going to be the impedance Z. Oops, not like that. Equals Z. This stuff's really easy, right? Would you guys agree? Like, this is what your homework problems are like. They're really simple. It's just, you're just plugging numbers into these equations. It's what you're going to do when you go to grad school, or not grad school, engineering school, is you're going to realize that in engineering, all you do is plug numbers into equations. It's really easy by comparison with physics. And the only reason you learn physics is you have some kind of understanding why they are the way they are, so you can hold it in your brain, basically. But, yep. Equations and numbers, yeah, the old plug and chug. Okay, so we've got XC here, we've got XL right here. Let's label what they are, because we're going to want to use them later in case I forget what was what. Okay, let's circle our answers, as we do. Okay. And then next is to find the maximum current. Okay, which equation do I need for that? I just need this one, right? I have Z, so I take V max, which was given, divide by Z, and that's going to give me I max. So maximum current is going to be, what is it, 150 volts, divided by Z, which was 512. And it looks like that's going to be something like 0.4 or something, maybe? Oh, 0.293, okay. Do you guys agree? Only one person answering here. No, that's not true. 2 of you guys are answering. Does that one look right? Let's see. 150 over 500 would be 3 over 5. Or, yeah, 0.3. Okay, that looks right. Yep. Okay, next, what is the phase angle between the current and the voltage? That's given by this expression right here. So the phase angle between the current and the voltage is going to be the arctan of XL minus XC divided by R. Was it supposed to be in degrees? You can put it whatever you want, actually. We're going to do it in degrees, probably. What did you get as an answer for this? So XL was 471 minus XC is 757 divided by R, which is... Thank you. Should get a negative number, right? Negative 34 degrees. I think that's actually stated in the last part of the problem. So that's your phase angle. Oh, one thing I didn't mention, by the way, is if I want to write the voltage of the source as a function of time, this is going to be equal to V max multiplied by the cosine of omega t plus phi. That's something I left out. This is compared to the current as a function of time, which is just I max times cosine omega t. Right? So that's where that phase angle thing comes from. It's like, it's the amount that the voltage is out of phase with the current. In this case, it's negative 34 degrees. Okay. Part D, find the maximum voltage across each element. That's basically performing this operation right here. So for the maximum voltage across the inductor, we'd take this one and then plug in the numbers. So we've already calculated what I is, right? We want now the maximum values. Why is it not deselecting that? Whoa, man, this program's getting real laggy. So I wonder if I'm just running into RAM issues. So where's I? I is here. So it's 0.293 multiplied by x sub L, which was 471. And out of this, we're going to get, it looks like 138 volts. For VC, it's VC is equal to I times XC. So that's going to be the same current, 0.2. The equation for tan phi over, this is over R, because of this. So you make it VL minus VC over VR, but then you realize that VL is I times XL, VC is I times XC, and this is I times R, so all the currents cancel out of this equation, and that's why you get that expression right there. Yeah, good question. Okay, so VC is 293 multiplied by 471 was the XC, so XC is 757. This is 222, okay. Look at this, by the way. Isn't this interesting? Look at this number. Remember that V max, right, was equal to, what is it, 150? The maximum voltage across the capacitor is actually higher. It's actually higher than the voltage across the voltage coming from the source. It's kind of interesting, right? Okay. And what else do we need? Voltage across each element. The voltage across the resistor. It's the last one then. That's going to be equal to IR. And that is 0.293. God, this gets so repetitive. And I think this was 450. 425. Here we go. 425. Say 124 ohms. Or volts, sorry. Okay. And then part E. What replacement of value of L should an engineer analyzing the circuit choose such that the current leads the applied voltage by 30 degrees instead of 34 degrees, with all their values in the circuit staying the same? So if we want to do that, then what we're really solving for then is we have this equation that we want to say we want to force the phase angle to be 30 degrees, and we know that this is equal to XL minus XC divided by R. So what we can do is we can solve this for XL, right? If I say R times the tan of 30, this is something similar you guys are going to have to do in your homework, and then I add to that X sub C, that should give me the value of X sub L, but X sub L is equal to omega L, so to find the new value of, here we'll call it prime, the new value of the inductance that I need, I would just take R tan 30 plus XC, and I would divide by omega. So that's going to be, R was 425 times tan 30 plus XC was 757, and I divide that by omega, which is 2 pi times 60. Okay, and what do you guys get for this one? Wow, this is so weird. I'm actually writing on top of my thumb. And it's still picking it up. 2.65? And that is a problem involving Rlc series circuits. All right, do you guys have any questions? I'm going to add one additional question to this. Oh. I did something wrong in part E. Does anyone see what I did wrong? There's one error. Multiplied instead of adding. Well, I think what I did here is right. Something else is wrong. Multiplied like here. No, there's something else that's wrong. Maybe if I zoom up a little bit, you'll see what it is. Let's read the problem again. What replacement value of L should an engineer analyzing the circuit choose such that the current leads the applied voltage by 30 degrees rather than 34 degrees? If I go back to my picture up here, in this case the voltage was ahead of the current by an angle of phi. It's the angle. Yeah, what's wrong with the angle, Hunter? Or Tom? It's not XL and XC. What's wrong with the angle? Yep. It was negative before, right? So this one actually needs to be negative too. That should be negative, and that should be negative. That's going to change the answer, right? Yeah, I thought that answer was a little bit big there. What do you get now? Wait, you get 1.25 again? Really? Come on, no way. 1 second. Where's my phone at? 3.6. There we go. That sounds proper. Okay, there we go. Now, here's another question that we could ask. F. Probably a rounding error, Tom. I don't think that really matters. Suppose that we want to add a capacitor to the system to fix the phase angle to 0. What should the value of the capacitance be? We'll call it C prime V. And suppose we want to add a capacitor in the system, and our goal is to fix the phase angle so that it's 0. What should the value of this new capacitor be, and should it be added in series or parallel to the circuit? This is one of your lab manual problems. What do you guys think? The one in the problem. This one. This one here. So ignore what we did in part E. We saw that you can change the inductance to change the capacitance, right? But can we do something about the capacitance so that we can fix? Can we add a capacitor either in parallel or series and then force the phase angle to be 0? What do you guys think? Why don't you think about that, and we'll pick it up next time at that part. Okay? Sound good to you guys? We'll answer that question next time. You can think about it. We'll do it at the beginning of class, and then we're also going to talk about power in AC circuits and resonance in AC circuits. That's what we're going to do next time.